So, last topic we want to discuss in this course is vector graph theory. And I want to introduce some, relations between graph parameters and linear algebra. Yeah. So what was graph? Graph are the mathematical model that represents the binary relation among finite objects. So we have a finite object, and then we either have an edge between them or no edge between them. So that's a graph. So one natural idea is to encode this information about the adjacency into a matrix. So that introduces several definitions of this matrix, which are, useful in different ways. And in this way, depending on how you encode it, it has full information about the graph. So we can instead study about this matrix instead of the graph. And then here, get some understanding of this graph. Let's first define this matrix. There are several different ways to define this matrix, and then I will introduce a few of them. The first is the most obvious one, which is called the adjacency matrix. And we usually write A for this, A sub G, but we often omit G if it is clear from the context what graph we are talking about. So when we have a graph G, we assume that, so from now on, assume we have an n-vertex graph G on the vertex set bracket n. So its vertices are 1, 2, 2, n, the natural numbers. Those represent the vertices. And what? Then this graph, we define the adjacency matrix A, whose ijth entry is 1 if ij is adjacent in G, and 0 if not. That's most natural way to define it. So you just encode the adjacency information between each pair. If it is 1, then if it is adjacent, then you give 1, otherwise 0. Of course, in many different situations, for multigraph, you can add here the multiplicity of an edge, the number of edges between two pairs, or you can even consider weighted graph. So for each edge, you give some weight, which is some real number that you want to keep. That also makes sense. But for us, we just focus on this simple graph. So this is the adjacency matrix. And for simple graph, one thing you can see is that it has diagonal or 0. Because diagonal corresponds to the loop, but we don't have a loop. So this is a matrix whose diagonal is all 0. And then one more thing is that this is square matrix where the entries are symmetric. Aij and Hij have the same value. Okay, let's define other matrices as well. We can also define incidence matrix. Let's write B over graph G is a matrix on n by m matrix. Let's say the number of edges in G is m. So here you see that you have a matrix and each rows and column, the ith row and ith column correspond to the vertex I in this adjacency matrix. In the same way, you can consider the matrix, but now you have vertices here and then edges here in some ordering. I mean, it's not so important, but we fix an ordering over the edges first. So here, columns are indexed by the number of the edge step, and this is a matrix with ij entry. I mean, technically IE entry is 1 if it's I is incident with E, so it belongs to E, and 0 otherwise. So this naturally defines the information about the graph, and naturally contain all the information about the graph. Okay, one thing that you can notice is that but if you have this incident matrix and then it's transpose, and you just multiply, then you actually get the adjacency matrix. So this is easy to check. And also we define the degree matrix. And we write T of G is an n by n matrix with the entry Tij is degree of I in G if I and J are same, otherwise it's 0. So this is simply a diagonal matrix where the i's diagonal entry is the degree of vertex I. And lastly, we also define what's called the Laplacian matrix. And we usually write it as L of G is the degree matrix minus adjacency matrix. So these are some of the associated matrices we consider for graph G. Okay, so we will first notice that our main interest is the adjacency matrix and the Laplacian matrix. And this degree matrix is, mainly its purpose is to define this Laplacian matrix. And at least in this course, we will not deal with this much. And incident matrix also, we will not deal with this too much. So our main focus is this adjacency matrix and Laplacian matrix. And for these two matrices, if we think about it, it has something in common. One of them is that they are square matrix, n by n square matrix, and also they are symmetric matrix. Its ij entry and ji entry are the same. So this is real symmetric square matrix. And from linear algebra, we know that in this case, it has eigenvalues are all real. So all eigenvalues are real. It's diagonalizable. And there are orthonormal bases of eigenvector. So from this, we can obtain the following spectral field. So if M is an n by n real matrix, real symmetric matrix, in particular, we are interested in this Laplacian matrix and the adjacency matrix. If it is one of them, you know that it has real eigenvalue. say mu1 to mun in decreasing order, and n mutually orthogonal. You need an eigenvector. Say u1 to un. Such that the m ui is what? Mu I and mu I. Okay, we will not prove this, but this is, not so difficult to prove from this linear algebraic fact. Anyway, one thing is that here, some eigenvalues made it. So, for example, how you obtain this eigenvalue? You find the, corner of this, corner of the determinant of x minus I minus m, and that could have a dimension bigger than 1. Then some eigenvalue may be it. And in such a case that the corresponding eigenvector may not be unique. So there are more choices, more than one choice of this eigenvector. But anyway, so this gives us that this real eigenvalue is an eigenvector. So let's just assume that for this graph G, let's just, in most of our discussion, we will be given a graph n vertex graph G, and for that, this eigenvector, adjacency matrix has eigenvalue, say mu1, which is the biggest one, and to mun, and corresponding eigenvector, which are, unit eigenvector, which are orthonormal. Let's write this as a mu vector u1 to un. Let's write it with a superscript, because I want to write a subscript to denote its coordinate. First coordinate and second coordinate, because these are vector. We can talk about its ith coordinate. And also Laplacian, let's say it has eigenvalue lambda 1, lambda 2 to lambda n in an increasing order. Okay, why is this a decreasing order and why is this an increasing order? There are some relation between these two. Let's say if it's deregular, then what? If Laplacian is nothing but the diagonal matrix minus a g, and this degree matrix is nothing but the d times I in deregular case. So we know that the lambda I is d minus mu I. So this actually corresponds to lambda I, the smallest one. This biggest one and last smallest one are corresponding, and this corresponds. They correspond. To keep this correspondence, we write it in increasing order for Laplacian and decreasing order for adjacency matrix. Okay. So there are other observations that we can immediately see. One of them is that this lambda 1 is 0. Why? If we take, say, let's write as 1 sub s be the characteristic vector of s, or indicator vector of s, which has this is a vector whose I coordinate is 1 if I is in S, 0 if not. And then let's just write 1, hold 1 as a indicator vector for everything. Then one thing you can easily see that if you multiply LG with IN, so let's say 1, so KAIST vector or 1 vector, then what? You can check that this is actually 0, because what? Its I's coordinate is G1 minus A, one's I's coordinate is what? Degree of I minus, what's this? This is summation of Aij, I say entry of A, where J is the neighborhood of I, which is again degree of I, so 0. So this is it shows that this is all 0 vector. Okay, so this only tells that one of these eigenvalues is 0. But we can further show that this LG is positive semi-definite. Which means that all eigenvalues are non-negative. Then it shows that this 0 must be a smallest eigenvalue. So lambda 1 is 0. And then to show that this is positive semi-definite, what? You assume that let's say B is an eigenvector with the eigenvalue lambda. Then what we can prove is that what? You take the norm here and then multiply lambda. It's same as B transpose times lambda times B. Because this is what? This is inner product of B with the B. This is the norm. And as this is the eigenvector, this is L times B. And this is what? Summation of B transpose D times B minus, no, not summation here. You get this. Then, but you can prove this. So this is what? Summation of degree I times the BI square minus summation of I here, summation of I comma J, and you take Aij, Bi, Bj. And you can check that this is indeed actually same with the Aij times Bi minus Bj square over all Ij, where, yeah, all possible pairs of Ij. So these two are same. Why? I mean, you can compute it. Then this is what? You take Aij and then Bi pair, you sum it, and then you just, if this is 0, then that disappears. You just sum the values when this is not 0, which is 1. When this is 1, what does it count? That's the number of J, which is adjacent to I. So this appears exactly degree many times. So you will get it. And also what you get minus the twice of Aij, Bi minus Bj. No, sorry. So here you only add in this manner. Yeah. So here this is for all Ij. and then let's set it in this manner. Then you have a this term and this term corresponds to this. Then this part actually corresponds to this part. You will see. Okay, so from that, what you know, this is non-negative. So lambda is non-negative, so it is positive semi-definite, and lambda 1 is 0. Okay, so we have this so far. And okay, so now we want to study the relationship between this eigenvalue and some graph property. One of the key observations is that we can use this eigenvalue to study about the edge distribution of the graph. And the key reason why we can do that is the following. When we have a graph G, and then we have a vertex at S and vertex T, which may intersect, and we can write this EST as the number of edges between, let's write it this way. This is S comma T, where the S is in S and T is in T, and ST is in H. So you count the number of edges between S and T. For one thing is that if S and T are here, then S comma T and T comma S are both counting. So this may double count some edges. But if they are disjoint, then it's counting everything once. And if they are identical, S and T are same, and then everything is counted twice. Anyway, so once we write it this way, then what we can easily see is the following. So for any vector x and y, any real vector, what we have is that we can compute this quadratic form. And this is what? This is, you can compute it in a way that for each, so this AG part, its entry is 1 if and only if I and j are adjacent, otherwise it's 0. So if we compute this quadratic form, the multiplication with the non-H1 are all vanishes, and then only remains are this one. We take I, j, which are adjacent. We take the i's coordinate and j's coordinate, and then you multiply and add. In fact, in particular, for say sets S and T, we have that the number of edges between F and T is that you take the characteristic vector for this S and characteristic vector for this T, and then you take this transpose and then you multiply these three, and this gives you exactly this. So this is about the edge distribution, and this is the quadratic form we get from the matrix. And then this is closely related to eigenvalue. So by studying eigenvalue of this, we can extract some information about edge distribution in this graph. Okay, so with this motivation, we will define this something called the Rayleigh quotient. So we say that the Rayleigh quotient of vector x with hat to a matrix M is what? Is you take the transpose and then multiply with M and X, and then you divide it by X transpose and X. So on the bottom, it's same as taking inner product with X and X, which give you the known squared. And this is actually, I mean, important as the our matrix M is you can consider it as an operator, X to M X. So this matrix is corresponding to this operator. And then this operator, we want to, study its geometry. Then much important thing is that when we have certain vector, if we apply this operator, then how much does it expand? Or how much does it shrink? Or how much does it rotate? So that's kind of an important thing. So distance from Rn to Rn in square one. So, and this Rayleigh quotient, in a way, measures how much those vectors expand. And then that's closely related to eigenvalue. And the following Courant-Fisher theorem provides such relationship between this Rayleigh quotient and eigenvalue. So let M be symmetric matrix with eigenvalue. So real symmetric, right? Yeah, we only consider the real matrix. Everything is real here. Then what? Alpha K is same as the solution of this integer program. This solution of this maximization problem. You consider arbitrary k-dimensional subspace S. Then you consider some non-zero vector there. And then you consider the minimum of this Rayleigh quotient. And that's same as alpha K. And in the similar way, you consider all possible subspace of dependent n minus k plus 1. And then for that choice, you consider the maximum choice. Of M, X, which maximize the Rayleigh quotient. And that's same as alpha K. So for example, what does it say with 1? If K is 1, then here is what? This is maximum of this one-dimensional space. And then once we have one-dimensional space, this vector is, essentially unique. So here, if you see it, so if you multiply some constant on X, then some constant C on X, then this value and this value both increase by, multiplied by C squared. So this Rayleigh quotient of X and Rayleigh quotient of some constant times X are the same. So you might as well just consider unit vector X. And if you choose the one-dimensional space, there is only one choice of unit vector. Technically two choices. You can take the negative of the other, but they give you the same value. So that this is fixed. So this minimization part is not necessary. That means that out of all unit vector, the maximum of this Rayleigh quotient value is alpha 1. In the similar way, so for whatever subspace you take, so this part is at most alpha K. So this shows that by finding maximum or minimum value of this Rayleigh quotient, you get the eigenvalue. And on the contrary, if you know the eigenvalue, then you can bound the value of this Rayleigh quotient. So, yeah, let's just prove the first inequality. First equality. So this one is, almost, similar proof work, same proof work. So we just consider it. So as we mentioned, we can only consider unit vector X. Okay, so let's say you have this eigenvalue, and then let's say this you have a corresponding eigenvector. Also normal eigenvector. So, but now we proved it in both directions. So first we prove this direction. And what we have to just show that there is a certain choice which yields this inequality without this maximum. So we fix that. So let Sk be the span of P1 to Pk. Then what? For any vector in this span, we can write this as a summation of ai pi with its norm square is same as ai square, which is 1. So this is for any normal unit vector x, we can write it this way. And what's this Rayleigh quotient? This Rayleigh quotient is nothing but you can just compute it. AI times AJ times PI transpose M PJ transpose. Then what? So this is eigenvector, so alpha J, PI transpose, and then PJ transpose. Because PI transpose times PJ, this is inner product of those two, and then this is also normal. So this vanishes when I and J are different. The only remaining one are when I and J are same. You have this. This is what? So the square of AI sums up to 1. And then alpha 1 to alpha k are all at least alpha k. It's and most alpha k times summation of AI square, which is alpha k. So this just proves that we find specific choice of S so that this one is at most alpha n. So the specific choice which give you the equality, that means if we choose the maximum one, then this inequality holds. Okay? For the other inequality, it's also essentially same. But let B be any k-dimensional subspace. So now what we have to show? We have to show that for this direction, for whatever k-dimensional space we take, we can find the, x which minimize this so that this is at most alpha k. So now what we do? Let S be the span of pk and pk plus 1 at the pn. And what? And dimension of B is k, dimension of S is n minus k plus 1. And these two sums up to number bigger than n. So there exists a non-zero vector x, the non-zero unit vector, that lies in both of them. And this x is in S, so this is summation of AI pi, where I is from k to n. So you can write it this way for some AI with the summation of AI square. This one. And as before, you can again compute this this regular quotient, then that's what? Summation of alpha I AI squared. But now what? In this order, alpha k is the biggest one now. So this is at least alpha k times summation of AI squared. And what? You get this. This shows the other direction. So we have the equality, and that proves this Coulomb-Fisher theorem. Okay, so now we have collected. We have to make some. We have defined the important notation and these eigenvalues. Now we want to explore about the connection between them and some graph property. So first, in the next video, we will talk about the connection between the density of G, the denseness of G. So it means how many edges does G have, and the largest eigenvalue of oscillation matrix. There are some relation between them. We will talk about that in next video.